So, and the next talk is about energy efficiency, because I'm reasonably good putting a flow together now that you speak. So, my pleasure to introduce you to Tevfik Kosar from the University at Buffalo. And he will, okay, yeah, he is all good.
Yeah, thank you, Nick. And thank you for the invitation. It is a great pleasure to be here. This is my first time at Multicore and also first time in New Zealand. So I have been truly enjoying it so far. Good afternoon, everyone. So for those of you who don't know me, I'm Tevfik Kosar. I'm a professor of computer science and engineering at the University of Buffalo. My research focuses on distributed systems and how to improve the performance, scalability, and energy efficiency of distributed systems, which are all very, very well connected to each other. And these days, almost all computing systems are distributed, so it applies to many different areas of HPC, cloud, data centers, and so on. I also served as a program director at NSF, Office of Advanced Cyberinfrastructure, a couple of years ago. So many of you may have interacted with me through that. Just to leave it here too. And something that you may not necessarily know about me. Okay, hopefully this will work. So I'm from Istanbul, Turkey. And Turkey is very conveniently located between Europe and Asia. And the city of Istanbul, it is probably one of the few, if not only, city in the world which spans 2 continents. So we have the map of Istanbul as you see the city, and there is a very thin strait. This is a beautiful piece of sea as you see here, which divides Europe and Asia. And there are multiple bridges on this sea, on this strait, and they connect the continents. And when you cross the bridge, one way to the other, it says, welcome to Europe or welcome to Asia, which is very nice. I'm from the western side of the city. I'm from the European side. And my wife is from the eastern side, which is the Asian side. And we constantly argue about which side of the city is the better side. So there is no winner on that. And maybe one funny thing I remember is, so when we were dating with my wife, like 20 years ago, every time we wanted to go out, so I had to I had to take an intercontinental trip to pick her up from European side to the Asian side. So that was really fun and also funny if you think of that way. So basically, so let's go out today. So why not? I just need to take an intercontinental trip for that. All right. So this is something maybe you couldn't really find on Google about me. And about today's talk, I think Nick really did a great job. So Jeff's talk was an excellent prequel to my talk. He mentioned about the demand for computing, how it increases, and how it is potentially the most important bottleneck in front of scaling computing further. And I will follow up on that. So many people in the conference so far, they talked about the power demand of computing, especially power demand of data centers. But something was not mentioned much is there are other components of computing, for example, networking and data movement, which enable computing. So we didn't really talk much about the energy demand for it, which is also very significant and should not be ignored. I will talk about our efforts on making networking and data movement more energy efficient and scalable. I will also talk about how we use AI to enable that. So this may sound like a contradiction. So you are using AI to make something energy efficient, but I will explain how we do that. Okay. So I will just start with some numbers. Some of you maybe you already know, but IT industry overall, according to recent statistics, it uses around 8% of global electricity. But with AI and other emerging demands, it can reach up to 20% by 2030. Basically, very soon, since it is exponentially increasing. So this has three important implications. One of them is the cost of power. Cost of power is important. It is measured in the order of hundreds of billions of dollars, basically to power the entire IT industry, which is really a great number. So the entire IT industry is trying to bring that cost down. So this is one aspect. The second aspect is also, of course, about the climate impacts of power and computing. The carbon emission of IT industry overall, it is around 3% of global emissions, which may not sound too much, but which is actually very comparable to the carbon emissions of the aviation industry. So think about all of those planes and the carbon emitted by those planes. They're very similar. And if no measures are taken with the demands for new data centers and so on, the carbon emission of the IT industry is expected to reach or maybe even exceed 18% of the entire global carbon emissions by 2040. And the third implication is something already Jeff mentioned, and I also mentioned in the beginning. The scarce energy resources can be a limiting factor for scaling of the entire computing industry. So this is very important. Now, when we talk about this 8% share of IT in the world's electricity usage, so where does the power actually go? And of course, we know data centers, HPC centers, supercomputers, they take the largest share, which is around 40 to 45% of power goes to power the data centers. But another component we generally ignore, which is the networking component. It takes around 30%. It consumes around 30% of the global power usage. And this number does not include, this is only the power consumed by the routers and switches which power internet and interconnects. It does not include the NICs on our devices or NIC-to-NIC connections in data centers, etc. I mean, if you add those numbers, this actually goes up a lot. Okay? And the data movement alone, it consumes over 100 terawatt hours. I mean, we are talking about the megawatt hours required for powering data centers, but also powering these router switches. It consumes over 100 terawatt hours energy annually. So there was a recent study which I would also like to add here. So they did study the carbon impact of sending several hundreds of terabytes of data through network from Europe to China versus sending the same amount of data via disk in an airplane. And the result of this study was the studies cited here. Sending data via plane is actually a couple of orders of magnitude less carbon emitting compared to sending over the communication network. I mean, this is something as a computing industry and research we need to think about. Okay, so this is the background, and of course, power-aware networking, carbon-aware networking. This is not really a new research area. There's a lot of research in this area going on at the hardware level, protocol layer, at the application layer, and so on. So there is a lot of work on, okay, if you are not using a switch or a router or a certain node in between and so on, you can just put them to sleep, or you can adapt the forwarding rate of the network devices and so on. There are also a lot of work on protocol layer, such as power-aware network protocols. So these are all promising and, of course, give very, very interesting results for the future. But the issue with some of these approaches is research to production may take a long time, especially in the context of networking. The IT industry is generally very well motivated to increase the energy efficiency of their data centers, but not necessarily the same for ISPs, replacing all of their routers or switches with more energy efficient ones. So this can be either a too costly investment or sometimes not practical. For example, if you consider TCP, you can come up with a much more energy efficient version of TCP. But what would it take to replace TCP today, for example? Sometimes it's not practical, although there are very interesting work in this area. So in this work, what we claim, and actually what we show is, in addition to all of this work which is going on at the hardware level, protocol layer in the networking stack, there is significant amount of power saving that can be achieved completely at the application layer, since the way we use these networks, it is very, very inefficient. I mean, those of you who have worked with data moment or with networks know, I mean, using any single data transfer tool, even getting a high performance from the network is very difficult. It's not easy task, correct? And making this energy efficient is much more complicated. But so there is a lot of space for improvement. And we also claim that we don't only increase the energy efficiency, but also we don't sacrifice from performance. So we can achieve both high performance and high energy efficiency at the same time. And the reason is the existing solutions are highly inefficient. This is why. Right. Okay. So how do we do that? So there are many application layer and kernel layer parameters which are impacting the performance and energy consumption during data transfer. And all of these can be tuned at the application layer without making any change in the entire stack. And this includes number of TCP streams that you want to use for the transfer, number of threads you want to run at the end system, the pipelining between data transfer commands, or number of active CPU cores you want to use, or CPU frequency scaling. So these are some of the most impactful ones. There are, of course, other parameters which impact, but we focus on these specific 5 since they have the most impact on both performance and energy efficiency. And of course, these parameters, they are very well known. When you increase the level of concurrence or pipeline, you increase the performance of something, correct? So this is not new. But what is not known or what is not studied well is the energy performance trade-offs. Basically, if I increase the level of parallelism in my system, how much performance do I get versus how much more energy I consume? And where is the right balance for this? So we studied that in this work. So this is just one example. Now, of course, most of these parameters, they may have different impact on different data sizes, different network conditions. This is just one example. Here, we see the blue line here is level of concurrency, basically how many threads you run and how many data transfers you perform at the same time. And you increase the level of concurrency and you expect the throughput. When you increase the level of concurrency, you expect the throughput to go up to a certain level. But we also know that when you increase level of concurrency, meaning you increase number of threads running, you increase the CPU utilization, the instantaneous power consumption goes up, correct? So all of the 5 parameters I mentioned, their impact in increasing the performance, which comes with increasing the instantaneous power consumption. Okay, but also we know that the energy consumed is power times time. So basically, while the instantaneous power consumption goes up, the area underneath it, the energy can be potentially minimized, correct? But this is not really a simple problem. And the reason for that is the hardware components like server network hardware components are not energy proportional. So when you double the usage of a hardware component, when you double the performance, your energy consumption does not double. Correct? So you need to find the fine points where you increase the performance, but meanwhile the power consumption, the energy consumption is actually minimized. If the increased power consumption does not really pay off well to provide additional increase in performance, then it's not really worth it. So this is in one sense an optimization problem to find these fine breakpoints. The traditional optimization solutions, offline optimization solutions, are not very well for this problem, since data transfer optimization, it is a dynamic problem, correct? So during the runtime, there is background traffic, so you never know what the available bandwidth will be for you. So that means you need to do both offline optimization and online dynamic tuning, so which makes this problem a very suitable fit for AI. So you can use AI model, especially reinforcement learning models, to solve this problem. So, but when you optimize using an AI model, so there's two questions that you get. First of all, what will you minimize or maximize? Correct. So just minimizing for energy is not a solution, since when you minimize only for energy, you can get a very poor performance. So you don't want to do that. Correct. The second question is, will it really work using an AI or ML model to achieve it? I mean, what will be the cost of it? To answer the first question, instead of simply minimizing the energy or maximizing performance, we come up with what we call service level agreements, SLAs. So that means, so one user can have a performance constraint. So I want to achieve such and such bandwidth, but while guaranteed, so you can try to minimize energy consumption to achieve that bandwidth. Another user can have energy constraints or energy budget. So I have such and such energy budget. Using that energy budget, can you maximize the throughput I get? And the third one is how can you maximize the throughput or amount of bytes sent per watt used, correct? So we doing optimization based on these three SLAs, and so we use a DQN architecture. I will not go into details of this, but I will highlight what the takeaway points of this is. Of course, when you use an architecture like this, there are so many parameters which can take hundreds of different values. So you have what we call state space explosion. There are hundreds of millions of different states. In today's world, with LLMs of billions of parameters, you can say what is the problem. Since we want to minimize energy consumption, solving a large model like this would not serve the purpose. So what we do is we do state space decomposition. So we decompose the state into smaller, more manageable components. And in order to achieve that, what we do is we do what we call hierarchical clustering. I will also not go into detail of that. We use agglomerative hierarchical clustering. So based on the data we have, which can be for the exact same source and destination, and all of the parameters being the same, so your past performance may have been different due to the background traffic. Correct. So we create the clusters based on potential background traffic patterns, and then we feed each of these to a different mini DQN architecture. And meanwhile, we also do data reduction, since you realize some of the layers, some of the clusters that you created may not be really relevant. So it is minimizing or reducing the amount of data and states, but also it is making the DQNs more manageable, with more efficient. So this solves the problem that we are dealing with in two aspects. One is it addresses the state space explosion issue, which causes excessive training time. But it also solves the problem of the need for access distributed data sets. Since when we talk about data transfer optimization, some data can be already distributed in different nodes. Instead of moving the data around for training purposes. So you can run each of these mini DQN architectures on different nodes where the data is actually located. So that also helps with that. So that provides a very, very efficient, very lightweight solution, minimizing the energy footprint of training itself. In terms of the application areas, it is very broad. So you can apply this to inter-data center replication for cloud-hosted web services, for mobile IoT, edge-to-edge, edge-to-cloud data transfers, and so on. And we did apply it to all of these areas. I will just share the results from one of them to give you an idea of how much energy can be saved. So this is for cloud-hosted data transfer services. And the two bars on the right you see are our solution, what we call green data flow. And as you see, so we can achieve both high performance and low energy at the same time. And it can provide up to 60% lower energy consumption with over 2x throughput efficiency compared to state-of-the-art solutions. So you can, for the exact same transfer, you consume less and actually you perform better. And again, the main reason behind it is the existing solutions are highly inefficient and they are not tuned well. Okay, and we are now also considering the carbon intensity of data transfer and how to optimize for that, which is another problem. I will not go into details of that, but we can discuss it afterwards. So the bottom line, the energy consumption of network and data movement is very significant, and we should not ignore it as a community. Okay, so it is not all about computing or data centers. This is important, but also this is an important component we should focus. Hardware layer, protocol layer solutions are good, but there is a lot of space for improvement at the application layer. So there is a lot of improvement we can make. So let's also benefit from that. Energy efficient data transfer optimization is a very suitable problem for AI, ML, since there's a lot of data available, very easy to collect data. Each data center or HPC site, they're already collecting a lot of data transfer information and logs. And instead of using one big AI model, we should prefer a cluster of smaller models for efficiency purposes. So this goes back to Dan's keynote from Monday, basically one big horse versus 1,000 of small chickens, and this also applies to AI models. So we don't really need one big giant AI model for everything, so we can use a collection of smaller models, and I will just stop here.